everybody, this is Miss Bufford, and in this video we're going to talk about radioactive particles and decay. So your learning goals for this video are to be able to describe the characteristics of alpha and beta particles and gamma radiation, and to be able to balance nuclear equations. So before we get started though, I wanted to make a clear distinction between the types of reactions that we're going to be learning about for the rest of this year and the types of reactions that we're just going to be learning about in the next two building blocks. So the reactions that we're going to be talking about for the rest of the year are chemical reactions. And in a chemical reaction, atoms don't change their identity. For example, a gold atom is going to stay a gold atom. But what changes is the way that those atoms are arranged with one another. So in a chemical reaction, atoms will rearrange themselves into new chemical substances or new chemical compounds. But in a nuclear reaction, we have what's called elemental transmutation occurring. And this is where one element actually changes itself into another element after it experiences some kind of nuclear event. And these elemental transmutations can occur through either nuclear decay or fusion or fission processes. And we're going to talk about nuclear decay in this video, and then for the next building block, we'll talk about fusion and fission. But no matter what type of reaction we're dealing with, all reactions are going to conserve matter. And so matter is not either going to be created or destroyed in these processes. All right, so what is radioactivity? This is various types of emission from the nucleus of an atom that can be due to several different factors. It can come from an instability in the nucleus that results from having too large of a mass, or it could be caused by a deviation in the ratios of protons and neutrons from what's called the magic numbers. And so there are configurations for the nucleus where we have a ratio of protons and neutrons that are stable, and we have unstable ratios. Whatever the case though, atoms undergo nuclear decay in order to just achieve a more stable nuclear configuration. They just want to be stable. All atoms with atomic numbers larger than 83 are going to be radioactive by nature. Elements with atomic numbers less than 83 have stable isotopes, but most also have at least one radioactive isotope. So in this video, the three different types of radioactive emission that we're going to talk about are alpha particle emission, beta minus or beta particle emission, and then gamma ray emission. Right? And there's just some information on here, but we're going to come back and talk about all of this information as we talk about each type of emission. All right, so alpha decay occurs when the nucleus of an atom is too large for the strong nuclear force to hold it together. And so atomic nuclei are held together by a special force called the strong nuclear force, and it's one of the four fundamental forces in our universe. The other forces are gravity, electrostatic attraction or forces, and the weak nuclear force. But the strong nuclear force's job is to hold together all the particles in the nucleus. And it works on a super tiny scale, which is the scale of the size of the atomic nucleus. And so if a nucleus gets too large, then the strong nuclear force has a hard time holding all those particles together, and then the atomic nuclei become unstable and they start throwing out radioactive particles. And some of those particles are alpha particles. And we write alpha particles using this symbol right here. All right. And we always indicate that the mass for an alpha particle is 4 atomic mass units, and the atomic number is 2. And we also can use the symbol for helium, because this is the same as a helium nucleus. A helium nucleus has a mass of 4, and it also has 2 protons. All right, so either one of those works to describe an alpha particle. Some characteristics are that it has a +2 charge. So when this alpha particle is ejected from the nucleus of an atom, it has no electrons, but it does have 2 protons, and so it has an overall charge of +2. And it is a low energy particle, and it's rather large, and so it's easy for this type of radiation to be blocked very easily by a sheet of paper or some clothing. But it does have a strong ionizing ability. And remember when we talked about ions, an ion is an atom that has more or less electrons than the number of protons it has. If it has more electrons, it'll have a negative charge. If it has less electrons than the number of protons, it'll have a positive charge. And in this case, when this is emitted from the nucleus, it has no electrons, and so +2 charge. And when it leaves that nucleus, it goes out with its big +2 charge, and it's gonna be very electron hungry, and it's gonna be hungry and eager to pull electrons off other things. And when it does that to satisfy its own need for electrons, it ionizes other things. And so that's why we say that this is very ionizing, because it's very hungry for electrons from other things. All right, so let's talk about how to balance alpha decay equations. When we write either a chemical equation or a nuclear equation, we always list our reactants over here on the left-hand side and our products over here on the right-hand side. And the reactants are always what we start with, and the products are always what we end up with. And so I'm going to start writing my nuclear equation with the nuclide symbol in here. So when we write nuclear equations, we use the nuclide symbol so we can see the changes that take place in the nucleus. And so remember, this A represents the atomic number or the number of protons in the nucleus, and Z right here represents the mass number or the total number of nucleons in the nucleus. And remember, the term nucleon is a collective term that means protons or neutrons, any particles that are in the nucleus. Okay, so when we have an alpha particle being ejected from an element, so here we go, here's our alpha particle, it's leaving, it's going to cause a change to that nucleus. It's going to decrease the atomic number by 2 because 2 protons are leaving. And then it's going to decrease our mass number by 4 because we have a total of 4 nucleons leaving, 2 protons and 2 neutrons. And so when we're trying to determine what this mystery substance is right here, we can do that by figuring out what the new atomic number is. And so if I take A and I subtract 2 from that, I'll get a new atomic number. And remember, those atomic numbers can be used to identify a substance. So we just look up the atomic number on the periodic table, and it will tell us which element that is, right? And then we also, on the product side, want to include the alpha particle that was ejected, all right? So this is showing the whole picture of what's happening here. So we start off with this radioactive element as one thing, and then it splits and that alpha particle leaves and we have a new element. And so our job is to identify this element and the new atomic number and the new mass. All right, so let's take a look at these examples down here. So here I have radium-226, and that's going to eject an alpha particle. So here's that alpha particle right here, and I want to subtract 2 from my atomic number, so I end up with 86 here. And I want to subtract 4 from my mass number, so I end up with 222 here. And so if I take a look at my periodic table, I'm looking for atomic number 86, which is right here, and that's radon. And we already see that in this example right here. But in a minute, you're going to have to know how to determine which element symbol to put there. And then for the second example, I'm starting off with uranium-238. And remember, an alpha particle is ejected here, and I need to subtract 2 from my atomic number, so I get atomic number 90. And then I subtract 4 from my mass number, so I get 234. And now I need to identify what this is, and even though it's already written here on the screen, I'm going to show you we're looking for 90 on the periodic table because that's our atomic number. And that is right here. So we've got thorium right here. All right, so let's go ahead. What I'd like for you to do is go ahead and pause the video and see if you can tell me or write down in your notes which element or which isotope of each new element we're going to have. So go ahead and write the nuclide symbols for the new elements. All right, so hopefully you were able to pause the video. You have a periodic table that's located in your OneNote notebook if you're one of my students, and it should be located under the reference material section. If not, you have one in this PowerPoint if you've downloaded a copy of the PowerPoint. And either way, let's go ahead and see how you did. So we're starting off with Lawrencium-256 here. It's going to eject an alpha particle and become Mendelevium-252. Right? Then we have proactinium right here, proactinium-231, and it's going to eject an alpha particle and become actinium-227. Right? So it's just, remember, we're just subtracting 2 protons from the atomic number and 4 nucleons from the mass number. All right, now we have actinium-225, and that's going to eject an alpha particle and become francium-221. And then we've got francium-211, and it's going to eject that alpha particle and become astatine-207. And then the last one, we've got gold-185, and it's going to eject an alpha particle and become iridium-181. All right, so hopefully you were able to get these all correct. If not, see if you can figure out where you went wrong. And if you're having trouble, please go ahead and send me an email so I can help you understand this. All right, so now let's talk about beta decay. Beta decay occurs when there's an imbalance in the number of protons and neutrons in the nucleus of an atom. And in this case, an atom has too many neutrons to remain stable. And a neutron in the nucleus will eject a high-energy electron, transforming itself into a proton. And you did hear that correctly. We're having high-energy electrons coming out of the nucleus. And so if we know that electrons don't reside in the nucleus, that seems really weird. But if you think about a neutron as a combination particle, so let's think of it as a proton and an electron together to form a neutral particle, then it makes sense that a neutron can eject that electron and then become a proton. All right, and that is called, that high energy electron that is emitted as a beta particle. And like I just said, so some characteristics of beta particles are that they are high energy electrons and they're shot right out of the nucleus. And they have a lot of energy, so they don't stay in that atom. They actually have enough energy to be ejected from that atom. They have a -1 charge because it's an electron. And these are, it's a moderately penetrating form of radiation. So it can be blocked by about 100 sheets of paper or by about 3 millimeters of aluminum. And it's moderately ionizing. So it's less ionizing than alpha particles, but more ionizing than gamma rays. So alpha particles are really ionizing because it's trying to pull in 2 electrons. Well, this is just one single electron that's out there trying to find a home. And once it finds its home, it's ionizing whatever it attaches to. All right. And so now let's talk about balancing beta decay equations. And so remember, in beta decay, we have that neutron in the nucleus that's ejecting a high energy electron, turning itself into a proton. And so when this happens, we're going to see an increase in the atomic number by 1 because one of our neutrons, it's turning itself into a proton. So now we have more protons. But the mass number is not going to change because we still have the same number of nucleons in that nucleus. So I've got my original element here. And the changes that are going to take place are I'm going to add 1 to my atomic number, but I'm not going to change my mass number. It's going to stay the same. Okay, so if we take a look at uranium-235 down here, if it spits out an alpha particle from its nucleus, then it's going to become neptunium-235. And one way that you can kind of check your work to make sure that you're doing these correctly is to take this arrow, which the arrow stands for yields or makes or anything like that. But if you think about this arrow as an equal sign, and you just think of this as a math equation, 93 plus -1 is going to be equal to 92. And so if you get that relationship there and it's working, then you're probably doing these correctly. So let's go ahead and do some examples. So I'm going to start with strontium-90, and it's going to eject that high energy electron from its nucleus. and it's going to become yttrium 90. Right? So its atomic number is increasing by 1, but the mass number is staying the same. All right, and if I have radium 228, it's going to undergo beta decay and become actinium 228. And then if I have carbon 14 and it ejects a high energy electron from its nucleus, it will become nitrogen 14. All right, so go ahead. Hopefully you got these correct. If you have questions, go ahead and write them down and we can talk about them in class. But now we're going to talk about gamma radiation. Gamma decay occurs when a nucleus is excited and it needs to release a lot of energy, or it's released during other radioactive decay events such as electron capture. So it can occur during lots of different types of radioactive decay, actually. I just chose electron capture because it's something we haven't talked about yet. So if gamma radiation is emitted alone, meaning the atom was just excited and it gave off a burst of energy, then we're not going to see any changes in the nucleus. All right, the element's identity is going to stay the same. But if it's emitted as a result or as a result of another type of radioactive decay, let's say electron capture, then in electron capture, we have a proton in the nucleus, so there's an imbalance in the number of protons and neutrons again, and this time, instead of a neutron becoming a proton is going to pull in an electron from the lowest energy level. It's going to pull it in, and it's going to turn itself into a neutron. Okay, and then we have a vacancy in this shell right here, so then we have all these electrons cascading down to fill in that vacancy. And as they drop down in energy levels, they give off gamma radiation. All right? So some characteristics of gamma rays are that they are very high energy waves. They're not particles, they're waves of electromagnetic energy, and they have extremely small wavelengths. So they can be very penetrating. They're very strong to penetrate. They have no charge associated with them. And they have very low ionizing power. And this is because even though they're really good at penetrating things, their wavelength is so tiny that it would have to hit an atom just right in order to ionize it. So they have very low ionizing power. So let's talk about balancing equations with gamma radiation. So again, if an atom is just losing energy and all it's giving off is gamma rays, then it doesn't change the identity. That atom stays the same. So uranium-235 here will stay uranium-235 if it's just giving off a burst of energy. But if electron capture is occurring, where that proton in the nucleus captures that low energy electron and turns itself into a neutron, then gamma radiation is going to be released during that process. And so when we balance these equations, we're going to start off with our reactants over here. So we've got the element that we're starting with and the electron it's going to pull in, because we have to combine those things in order to make our new product. All right, so this looks a little backwards than it did before. And the formula for that, for determining what our mystery substance is here, is that we're going to subtract 1 from our atomic number. Right, because we're taking away a proton now. Remember that proton's turning itself into a neutron, and then the mass number is not going to change by anything, right? Because we're not changing the number of nucleons or the number of total particles in the nucleus. We're just changing the identity of one of those. And so let's see this example here. I've got chromium-51, and it's going to pull in that high energy electron, and when it does that, it's going to become vanadium-51. Right, so you can see that the atomic number just decreased by 1. And again, in order to check your work with these, if you just think of this arrow, the yield symbol, as an equal symbol, and you think of this as a math equation, 24 plus -1 is going to be equal to 23. All right, so that's a way you can check your work with these. All right, so let's go ahead and do some examples. So go ahead and pause the video and use your periodic table to see if you can determine the identities of the new elements that are created. All right, so hopefully you were able to determine what you think is the answer. So let's go over the answers real quick. So I'm starting here with argon-38, and it's going to pull in that low energy electron and become chlorine-38. All right, and then I have strontium-80, and it's pulling in that low energy electron and becoming rubidium-80. And then iodine-80. Ooh, that's not, should not, yeah, iodine-80 is pulling in an electron and becoming tellurium-80. And then I have, I'm not sure what that element is. I forgot. It's thulium. I knew that. All right, we've got thulium-168. It's going to be pulling in that low energy electron and becoming erbium-168. And then I've got einsteinium-247 becoming californium-247. All right, so hopefully you were able to get these as your answers. If not, see if you can figure out what you did and figure out how to correct it for the next time. And please write down any questions that you have so that we can talk about them in class. Thank you for watching Buffered Chemistry. Subscribe to my YouTube channel for more chemistry help.